be will be sent to the first one who opened the Google Meet. I'm not sure. Is that you, Rivaldo, the first one who come? Or I think if not Rivaldo, it's Aisha, right? Yeah. So later, it will be saved. The file will be saved in your Google Drive. Maybe after the lecture, you need to open the file and set the share file to me so I can upload to the Google Classroom. Okay, but later. Okay, yeah, thank you. I forgot to record the meeting. Okay, I hope the chain rule here, you get the idea on how we are dealing with the chain rule. Okay. 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 Any? Yeah. You can say that this is the general version. Yeah. Okay. Now, I think that's all for the chain rule. You can check just the exercise later if you want to check your skills on the chain rule. Okay, the other thing is the implicit. I have told you this before, but let me just explain one more time. Implicit differentiation in calculus 2. Let me just review calculus 1 for implicit differentiation. You have y equal f of x, right? And example, you have y cubed plus y squared. Just make up the equations. Plus just 3 constant. Okay, if you want to find dy dx, so we can differentiate all the terms here with x, right? So when we differentiate y, because y is function of x, in implicit, we write this and we need to multiply with dy dx and every y terms. Okay, so plus 2y and then dy dx, and then minus 5 dy dx, and then minus 1 equals 0. And you can group all this dy dx and you can find what is the dy dx. Right? Okay, we can write this term, this equation, in terms of a big functions f, or just f like that. Let me write one more time this. Okay, and we can write in terms of 3 diagrams actually. So f, and then f is having x and y, and y is still having x. And this is and this is independent, and this is dependent, right? Y is depend on x, okay? And we can write Okay, if we want to differentiate with x. Oh wait, I don't need to write this, okay, because I already make 0 here. Okay. And then we can isolate dy dx. And this is precisely the same answer with our solution here. Okay. So we can also think the calculus 1 problem in terms of our chain rule tree diagram. And it will be the same results, which means our tree diagram, we can arrange as many as possible the variables. Okay. Okay. So let me give you another example, so you know how to use it. Okay. So this has become important to find the implicit. Okay, another example. Let's say we have 3 variables. Okay, same thing as this f here. We can also make this function become a function's just f. Okay, and we write, and also we can write it's also 1. Okay, we can write the diagram. It's f and then x, y, z. Oh, sorry, I forgot to mention if this is if z is functions of x, y. I hope you don't get confused of this f. Okay. So z is having 2 variables, x, y. So this will be dou f dou x, dou f dou y, and then dou f dou z, dou z dou x, and dou z dou y. Okay. Okay. So for dou z dou x, we have dou f dou x plus dou v dou z plus multiply with dou z dou x, and it's equal 0. And for dou z dou y, we have dou f dou y plus and we can have and based on the equations, is the first equation here given. Dou f dou x, we just differentiate with respect to x, and the other will be a constant. So we will have negative 2x over 2z, or we can write negative x over z. And here is, we can isolate and it will be negative y over z, okay, based on these equations. Okay, let's say this is the first method. I'm not recommending the first method. The first method. What I recommend is the way that I give you, I think in the previous lectures. Okay, so when you have x squared plus y squared and z squared equal 1, and you want to solve implicitly, let's say you want to find dou z dou y, okay, right? From here, you can differentiate with respect to y. So okay, you can do it directly implicit. Okay. The thing is, you need to remember whenever you make this implicit in calculus 2, you will have more than 2 variables. It can be at least 2 variables, but it may have more than 1, more than 2. Like this one, it has 3. Right? It depends on the question given, the relation between the functions. So for example, if you have this, because it's y, so whenever you find y, you can directly differentiate, right? But whenever you find x, for example, you can write and differentiate x to x, but write dou x dou y plus 2y and plus 2z dou z dou y equals 0. And here is actually 0, right? This is just the same thing as when you differentiate partially, the other variable will be treated as a constant, and you can make it 0. This is what it means. Okay. So you will have 2y plus 2z equals 0. So dou z dou y is negative y over z. It's the same results. And this is, let me write, this is the second method. I prefer this method because you can directly write down this implicit based on your equations. Okay. While the first one, you can write this based on your tree diagrams. It's safer, but in terms of calculations, it will be taking some times to write. Okay, but here you can directly write the implicit. Okay. Okay. Any questions? No. If no, then we can move on to the next section. It's called the directional derivatives. Okay, let me move to the next slides. Okay, this will be directional derivatives and a gradient vector. I believe gradient vector you have maybe learned. The top part, this part, William? Oh, okay. Okay. Yeah, we still have 14.6, 14.7, and 14.8. That will be the last part of chapter 14, and we can move to chapter 15 afterwards. Maybe we still have, I hope in at least next week we can finish chapter 14 and move on to chapter 15. Because 15 is actually, the content is really heavy and a lot of sections. So I hope we have time. But maybe I will skip some parts and just mention the essential parts. Okay, you're welcome, William. Okay, now let's move to directional derivative and gradient factor. And this is the same thing in, I think, in physics, when you have functions and you write this triangle, but you write like this. It is called the gradient vector. Usually in the electric field, you will write the gradient vector, but let's dive in the calculus part. Okay, as a review, this is just a review and how to make the connection between all of this. If z is functions of x and y, and the partial at some point is defined as and the partial y, we can also have similar definition. Okay. And this we can write, represent the rate of change of z, because we can also write this as dou z, dou x, and dou z, dou y, right? In the x direction and y direction for this is for dou z, dou x, and this is for dou z, dou y. Okay. Okay, we have this in our first lecture in chapter 14. But now the problem, suppose we want to find a rate of change of z at a point, but in the direction of the sum factor. Of vector u. We have a unit vector. And how to do this? Let me take you to a picture that I prepared. Okay, let's see here. The blue one is the surface. Let me write this. So this is the surface S. Okay. You have a point P. So this is S with the equations z equal xy. And we let the z coordinate as coordinate in x0 and y0. And the point P is here. Okay. And we have, because we already define our vectors here in directions A and B. So let's say we have, this is the vector, okay, vector u. And if we are trying to make, so imagine we have C that is on our plane, our surface, sorry, C in our surface. And the vector u, we want to project the vector at some point here, the q and q prime. Okay, this is the projection. So we can find the length. Okay, I mean maybe right here. So we can find the vector p prime and q prime. This is scalar and then vector. Or we can write this as HA and HB. Okay. So why we have H here? Because we are projecting the component. Okay, remember in the chapter 12 vectors, you have projections, and you may have scalar scale for the scaling. Okay, so we have this, and we can make up the axis. For the x is HA, for y is HB. So actually we can write x minus x0 is HA and y minus y0 is HB. The change of rate, okay, the change of the length. Okay, so we can write this into this form. It's similar to a parametric, but it's a little bit different. Now, if we are writing this delta z, and see the difference with respect to h, okay, with respect to h, we can plug in the x and y as with having ha and hb, which is the vectors from the u. A and b is component vectors, right? And minus the initial point, still divided by h. And if we take limit as h getting 0, we will obtain the rate of change of z with respect to distance in the direction of u. Okay, this is what we call directional derivatives. So it is derivative, but it has a directions. Okay. Let me write in here. Okay, the conclusions of this part. So definition. The directional derivative of f at some point in the directions of a unit vector that's the directions is, okay, we write d like that, and we have small u, that's the directions, and f at some point is equal. The definition is using the limit definition as in our original derivative. Okay. This should be provided the limit exists. Okay. So what does it mean for this sign here? It means it tells us rate of change of z in direction unit vector u, or maybe right like that vector. I hope you understand this is the vector. Okay. Okay. And now, in relation with the partial derivative, we can also write this directional derivative in terms of the partial derivative. Okay, so we can simply let me move to the next section. Oh, is there any question from here? I think this is just the beginning. Let me continue first. Okay, so the theorem, if f has directional derivative in direction of a unit vector, u is equal AB, we can write the directional derivative as so this is actually f is differentiable. Okay, okay. So we can write the directional derivative. Actually, in practicality, in practice, you can write easily. So directional derivative. Okay, this is directional derivative. What you need to write is first you write the partial. You put the point, plug in x and y inside the partial, and multiply with the component of the vector. Okay, so it will result in or let me just give you example so you can have idea on how we are going to do some calculations. Okay, find directional derivative at point for function okay let make three variables. In direction, let's say we have a is okay that's the unit vector. Okay, first because it's just the vector, we need to find the unit vector. Let's say the unit vector is u, then this will be defined as this, right? I hope you still remember. So this will be 2, 1, -2. And the unit vector is square is 4, 1, 4. It's 9. It's 3. So it's 3. Okay. Okay, that's the first part. Let me write the functions. Now we can write the partial x. And partial y. And the partial z. And we can plug in the point. It's become -4. Select the point. Oh, wait. It should be wrong. Maybe write completely to avoid mistake. So here is 1. It's also 1. Now the directional derivative is -4. And then the component of the vectors, remember this is, and we need to divide this component into all this partial. So first is 2/3 plus so we get -3 as our results. What is the meaning of this in graphs, or what's the negative signs means? So negative signs mean f, the function is decreasing 3 units, okay, whenever f is going into direction of vector A. That's how we are define what the number means. Okay. Okay. Any questions first? So directional derivative is you derive it's similar with the partial derivative, but the difference is you need to multiply with the factors. You need to take component of the factors and make it into partial derivative equations. Okay. So basically, you can find the derivative when it has some specific directions of some vectors, and it can be in any way it's want. Okay, depends on the directions. Okay. Okay, maybe giving another point of view for example. Okay, let me give you another example. Find, if I write D and then U, F, this means that find directional derivative if the function and U is unit vector in the direction given by this angle. It's measured from x positive axis. What is directional derivative at point 1 and 2? Okay, so based on this example, we can start with partial first. So write the equation. Okay, whenever you find this partial directional derivative, what you can do first, although maybe you don't understand the whole question first, but you can just do the differentiations, okay, at some point. So you can find the partial x and partial y first, and then you can see the directions or the unit vector. Okay, at least we have the partials. Okay, we have the partials. Okay, now the direction is the tangent. I mean, the angle pi over 6. So we need to use cosine and sine. Okay. So because it's a unit vector, then, or let me write here. So x is r cosine. Okay. And the radius is just a 1 unit because we are going to make a unit vector. So it should be 1, right? So x will be, and y will be. So this will be our direction. So cos and sine. Okay. And we can put into our whole equation of the directional derivative. Yeah, we can solve this, but I think we can take the point -3. Yeah, now we have this much of unit, which means f will be increased as in the direction of, let's say the vector is just okay. Okay, that's it. The whole directional derivative. The next thing is actually it's still directional derivative, but we are using another term. It's called the gradient vector. Okay, any questions first? Okay, let me move to. So I think I can finish until all this gradient vector part because it's similar to the directional derivative. So let me write the directional derivative. Okay. Now we can take this and this and this and this into a dot product. And dot the A B, right? This is actually a dot product. Okay. Now this part here, this partial x partial y, in terms of vector, we call this is the gradient vector. Okay. And we can have the first theorem for the gradient vector. So if f is a function, let's say two variables, x and y, then the gradient of f is the vector function. We write that gradient as in this term. Okay, defined by the gradient vector of f or we can write in terms of the standard vector basis. Okay, that's the definitions. And directional derivative in this case means that we are having dot product between this gradient vector and the directions, the unit vector. Okay. Okay, let me give you an example. Okay. It's for this gradient. Let's say you have 3 variables. Actually, function of 3 variables will be the same. Or maybe let me write the definition first. Maybe for the 3 variables and more. This is basically similar, but you need to have, or you need to add one more variables and make it 3 variables. Provided the limit exists. Okay, so basically the same thing, but you need to add x, y, and z. So here, in the example here, if you have these 3 variables, let's say this is x sine yz. Okay, the question is need to find gradient of f. And find directional derivative at this point in direction of, okay. Okay, so basically we need to find the gradient vector. So we need to find partial x, partial y, and partial z. And we can find it by differentiating the equation here. So we have sine yz, and then xz right? And then xy, right? And unit vector. Okay, that's the unit vector. And directional derivative at 130, it become and dot the unit vector, right? So we can check the x, y, z put into the equations. This is 0. This is 0, so it's 1. Cos 0 is 1, but it's another 0, right? And this is 3, and this is 0 and 1, so it's 0, 0, 3. So you have 0, 0, 3 dot with the unit vector. you only have this. Okay. Okay, I think I can move on. One more thing, okay? One more thing on this 14.6. Is how to maximizing the directional derivative. So theorem, suppose f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative is the gradient factor in absolute value. Okay, and it occurs when unit vector u has the same direction as the gradient factor. Okay, and thus, okay, the conclusion, thus the minimum value is negative of the absolute. Okay. I'm just adding this the conclusions so that it's more clear. Okay, so when you have a maximizing minimizing problem, then you can always use this theorem. Okay, basically finding the gradient factor, and then we can make the magnitude, the length. Okay, because or let me write the example here. Suppose temperature at the point x, y, z in space are given by, so you have equations for temperature. So T in Celsius and X, Y, Z in meter. In which directions does the temperature increase fastest at 0.11 negative 2? The second question is when is the maximum rate of increase. Okay, so basically this is the equations. Okay, this is the equations. So first, you may differentiate and find the partial. I hope you don't mix up the partial with the regular derivatives. But it's the same way when you derive any functions. So you have this, and you derive becomes this, right? So the same thing, you will get something negative, and the same exact equation at the bottom. But you need to multiply with the partial. It can be with x, with y, with z, depends on the partial. So first you need to find the gradient of t, right? The gradient. You find the gradient and put in the point that you want to observe, and then the maximum rate you need is to take the length of the vectors. Okay? So it will result in the vectors, right? Here you need to just to plus all the squared form and then take the square root, and you will get the increase of the temperature, the maximum rate. Okay, I hope you can check this by yourself. Okay, the last example, and I think yeah, the next Wednesday I think I can finish until 14.7. Probably next week is 14.8 and chapter 15. We can start chapter 15 next week. Okay, so for today, actually, I'm planning to have the quiz. I'm already set the questions in your Google Classroom, but maybe wait until 9:43 or 9:44. It will be automatically posted. Maybe another 1 minute. You need to wait another 1 minute, and it will be post on your Google Classroom. So you can check your Google Classroom. I think 9:43, the information will be posted. Okay, and the chapter 14 today, I will stop until here. And now you can check the Google Classroom. Just please wait a few seconds. Yeah, you can check the Google Classroom. You can check the chapter 14, part 1. So I've assigned, and you need to have 15 minutes, okay, around 15 minutes to work on. You can find now, William, in the Google Classroom. It's just posted. Yeah. Okay, I hope you already opened the form and can start to work on. We can look for notes if you want. Yeah. But I hope you try to work on by yourself, okay? Because it's actually it's also exercise for you, okay, to prepare um, the final exam. Okay. Okay, time's up. And don't forget to click the submit form to submit form and turn in assignment at the Google Classroom. But just click the turn in assignment so that I can grade your score. Okay, it's finished. Finish. You can leave the meeting if you finish. Together, don't forget to submit the form. Click the turn in on the Google Classroom also. Okay, finish. It's already time's up. And you need to turn in the assignment on the Google Classroom so that I can see and grade your score. Okay, finish. If you submit it late, you will be deducted a little bit. Okay. And you can leave the meeting if you already submit. Yeah, you need to mark done. Yeah, you need to turn in the Google Classroom. Yeah, you can check the Google Classroom and then you can click turn in assignment or done, mark as done. Okay. So I can mark your score.